Supposedly you can now hear me. Is this working? Good. My voice is not so good at the moment, so I apologize for using this machine. So I want to talk to you about some work that I did over last time with various people. Joe Harris, Craig Hunicky, Bernd Ulrich, and it's closely related actually to work that I've done with Roya Beheshti, who's here. Though that part of the work won't come up so directly today. The question is one that I can state sort of abstractly as the problem of describing the complexity of the fibers of finite morphisms. So the general problem is this. You have some projective variety x. Let's say n-dimensional, contained in PR, just a fixed notation. And I have a finite morphism to some other projective variety, perhaps PS. Phi. Then I'd like to, is this legible back there? Jürgen, can you read this? Good. I'd like to be able to describe the complexity of the fibers of such a morphism. And of course there are many ways of measuring complexity. You might measure the degree of the fibers. You might measure other invariants. The one that I'm going to study today mostly is the regularity. So the fiber of such a morphism, if I take y in PS, then the fiber, that means the scheme phi inverse of y. Since it's a projective scheme, it has a Castelnuovo-Mumford regularity, and I'd like to know something about that. Excuse me? It's R. Thank you. Everyone knows n is equal to R. So the sort of general question that I'd like to ask is about the Castelnuovo-Mumford regularity. Of phi inverse of y. Of course, that will be some kind of semi-continuous function of y, and the easiest thing to say about it is that there must be a maximum value for some y. So let's ask, how big could it be? How could we describe the maximum value without going around and hunting for all the possible y's and just measuring them individually? So the problem is this. Describe the max of these numbers. Sorry, regularity of phi inverse of y. So, oops, sorry. One motivation for this problem, this is I think interesting in itself to see whether you could do that, but one natural motivation is the problem of bounding the regularity of a projective variety in terms of the degree. So that's the reason that I got interested in this. So an old conjecture of mine with Goto was that the regularity of x, if x is now irreducible and reduced, let's say, over an algebraically closed field, so geometrically irreducible and reduced, the regularity of x should be bounded by, roughly speaking, the degree of x, and then if x is non-degenerate in projective R space, you can say minus the codimension of x plus 1. That's certainly sharp if it's true. This is known and was proved by Castelnuovo for curves, at least for smooth curves, for singular curves, proved by Gruzon, Lazarsfeld, and Peskin. And then it's even true for connected curves, that was connected reduced curves, that was done by a student of mine. It's known for higher dimensions, mostly for smooth varieties and special classes of varieties. It's known for smooth surfaces and by work of Sejong Kwak for smooth threefolds in P5. And it's known for toric varieties of codimension 2, for example, by work of Sturmfels and Peva. There are a number of other very special cases which are known, but in general this is wide open. Now, one way you might try to prove it is to start by reading Castelnuovo's paper and see what he did and try to do that. And that's been a rather successful idea. Again, this is something that Professor Kwak did in his thesis and since then. And the idea is then to take the case, let's say, X smooth. Seems to work best there. Then you might try to do this by projecting X generically to a hypersurface in Pn plus 1. Such a generic projection is certainly a finite map. And then you can use any kind of bound that you have for the regularity of fibers to bound the regularity of X. That's Castelnuovo's basic idea. Now, what sort of bound for the regularity of fibers could you have? If you project a curve into the plane, then you get double points. So you have fibers of length 2, and the regularity is 2. There, any n points on a line have regularity n. If you project a surface into P3, let's say from P5, you will have at worst triple points. Now, triple points, if they're not collinear, have regularity only 2. But if you have 3 collinear points in a fiber, it would have regularity 3. And there are examples where even for nice non-degenerate surfaces in P5, if you project into P3, every fiber has every projection has a collinear triple point in a fiber. So 3 collinear points in a fiber. So in that case, regularity 3. So it's not unreasonable to hope that the regularity of the fibers of a generic projection of a smooth n-fold are bounded by n plus 1. So let me state that as a conjecture. In this setup, so project generically, let's say pi, the max regularity of a fiber of pi is at most n plus 1. Now I say it's not unreasonable from those two examples, but one should be a little cautious. You might say, well, it's also rather reasonable to say that the length of the fiber is less than or equal to n plus 1. After all, it was true for curves and surfaces. It's known to be true up to dimension 14, even through work of Mather. And what theorem about projective geometry do you know which is true up to dimension 14 and is false? Right? So that's almost a proof. Unfortunately, Lazarsfeld pointed out a few years ago that in high dimensions this is hopelessly false. That if you have a generic projection of a variety of dimension 56 is the first case where we know that there's a problem, then the fiber will have length, so there will be fibers of length at least 70. However, his construction produces only fibers, or potential fibers, we don't really know what the fibers look like, but the construction only shows that these fibers have regularity about, in that case I think it's only about 25, the fibers that he constructs. So we're far under this bound for regularity. So note, length, the max length of pi inverse of y goes to something asymptotically which looks like 2 to the square root of n. So much bigger than n plus 1. So just the fact that this is true for small values of n really doesn't signify very much. I'm going to get some water before I stop talking entirely. Good. Anyway, this is the motivation, and if one has a good principle for doing something like this, maybe you can use it to prove something like that. I can't do that at the moment, but one can hope. There are my notes. All right, so what can we do to describe this kind of regularity? So here's an actual result. So again, I'm in the situation, this is a theorem from a recent paper with Joe Harris, that I have phi from x to x is embedded in p r, and I'm mapping it to some ps, finite morphism. I'm going to state this in a rather abstract way, and then I'll try to make it more concrete afterwards. So let's let epsilon be the following funny number. It's supposed to be the infimum. In principle, it could be infinite, of the numbers e, such that the following map is surjective. You can look at H0 OP n of e, tensor, well, now we need some notation actually. A morphism like that, of course, has to do with a line bundle, the pullback of the O of 1 on PS, and the space of sections of that line bundle, V. And this PS is really P of V. And then I want to look at H0 OPN of E tensor sim T, let's say, of V, mapping to H0 of L to the tth power. V is sections of L, so sim TV is sections of L to the T. OPN of E there adds a twist by E. I have a map like that. So I want to look at the infimum of E such that this map is surjective for sufficiently large T. Okay. Well, that's a number you could at least hope to compute, except that you might wonder how large T has to be, really. But other than that uncertainty, it's a number you can compute. And the statement then is, let's see, where shall I put this? Then epsilon is not infinity. And the supremum of the regularities of the fibers is exactly epsilon plus 1. So that's a way of looking at all fibers at once in this sense. It's a excuse me? Yeah. Yes, thank you. You can tell that I changed my notation just before this talk. And the change hasn't taken effect yet. The system is still updating. Okay, so that's the basic theorem. And as I say, you might worry a little bit about how big T has to be. but I'll give you a bound for an effective bound for t in a little while, so one can actually make this computation. Now I want to connect this with a piece of algebra which I find extremely interesting, and after I explain the connection, the proof of this will be a little more obvious than perhaps it is now. Maybe you'll see already why this is true, but I think it'll be clearer from the algebra. So let me start again with an apparently unrelated subject, and that's a very beautiful theorem of Kotkovsky, Herzog, Chung, Kodialam, Chung Wang, a whole bunch of people contributed to this, as the statement I'll give. This is 1999. Kodialam, 2000. And there's a paper of Chung and Wang that sort of completes this circle in 2005. And they also looked at a regularity question. They proved the following theorem. Suppose you take a homogeneous ideal in a polynomial ring and a finitely generated graded module over that polynomial ring, and look at powers of the ideal times the module, and ask what the regularity of that looks like. So if I in, let's say, S, which is the polynomial ring over some field, in R plus 1 variables, M, oh, this is a homogeneous ideal, I should say. Homogeneous. M, finitely generated, graded S module. You should think about the case where M is the homogeneous coordinate ring of some variety. That's the most interesting case. And you look at the regularity of I to the t times m. Well, regularity can be defined in two ways. This is the same Castelnuovo-Mumford regularity. I said it before as if everybody, of course, knows the definition, but perhaps you don't. One way to state it is in terms of cohomology of sheaves. There's an original definition by Mumford, taking off from Castelnuovo's old argument. There's another definition by free resolutions. So in the style that Frank was talking about in the last hour, if you take a free resolution of this module, then and look at the maximum of the degrees of the generators of the syzygy, so the maximum twists, the maximum d's that appear in the free syzygy modules S of minus d, then essentially that's the regularity. You should subtract I from the maximum degree of the generators of the ith syzygy and take the supremum over I. That's the regularity. And of course, if you have some experience with resolutions, you'll realize that there's almost no relationship between the resolutions of these different modules for different t. So it's not at all obvious that this is a function of t that behaves well. But in fact, it's equal to td plus epsilon. It'll be the same epsilon for large t, for some t, some d and epsilon, and t sufficiently large. So the asymptotic regularity in this sense behaves extremely well. Now, that, of course, leaves a major question, three major questions. What's d? What's epsilon? And how big does t have to be? These are very natural questions. Only the first has a good answer. We have nice formulas for d. And it's a little messy to state in this generality, But for example, if m is generated in degree 0, all generators in degree 0, such as the coordinate ring of a homogeneous coordinate ring of some variety, and if I has all its generators in 1 degree d, then that d is this d. So this is essentially the degree of the generators of I, if you like, the essential degree of the generators of I. Epsilon, however, remains mysterious. We have no general formula for epsilon and no general bounds for how big t has to be. The proof is existential. It uses the Hilbert basis theorem, basically. It's part of the same theology that Hilbert made long ago. So I want to connect these two by telling you a very special case in which we do understand epsilon. So let's specialize everything to the case which I'm going to talk about. Let's suppose that, in fact, let's get rid of m just for simplicity for a moment and pretend m is just the polynomial ring S, and I is an ideal which is primary to the maximal ideal, so contains a power of all the variables, an irrelevant ideal in that sense. And what else do I need? And that I is generated by forms of a single degree d. So that's the simplest case. Suppose I generated by forms of degree equal to d. That's the first assumption. The second assumption is that I contains some power of the maximal ideal. It's called the maximal ideal script m, which is x naught up to xr, excuse me. And 3, I'll take m equal to s. And then ask what these numbers mean in that case. Well, first of all, what's the regularity in that case? That's the easiest one. The regularity of I, there's no more m here, the regularity of I to the t is simply the smallest power of script m, which is contained in I to the t. So we can rewrite this. I could use one more blackboard, but I see I'm not going to get it. We could rewrite this in the form regularity of I to the t is equal to td plus, let's call it epsilon sub t. I can always choose epsilon t to be the difference between the regularity of I to the t and td, so there's always such an expression. And then that's true if and only if I to the t contains the maximal ideal to the td plus epsilon t, and no smaller. It's not hard to see from the cohomological characterization of regularity that this is just another expression for the regularity in this very special case. Now, it's obvious from this that the epsilon t's are positive, because I, generated by forms of degree d, is contained in m to the d. So I is contained in m, I to the t is contained in m to the td. So if you want it to contain m to the td plus epsilon, you better take epsilon positive. So this is some sequence of positive numbers. And a slightly finer analysis shows that in fact epsilon t is bigger than or equal to epsilon t plus 1 for each t. So the epsilon are decreasing positive integers. That's an excellent sign for them to become constant after a while. And so that constant value is the value epsilon that we're talking about here. So epsilon t equals epsilon for t sufficiently big. Now, these two contexts that we've talked about have a common overlap. Suppose X was just projective space. That's certainly the simplest case here. How do you get a finite morphism from projective space to somewhere? Well, you have to choose a line bundle on projective space, and there aren't very many choices. You better choose one of the O of D's, and then you choose some sections, V, and that's just some forms of degree D. So an ideal generated by forms all of degree D, containing a power of the maximal ideal, that's really just a well-defined morphism on projective space. And any such morphism has to be a finite morphism. So this picture corresponds to a finite morphism. Let's see. So this over here corresponds to a finite morphism, P or I guess to PS, which I could call I sub D. After all, that's a space of sections of a line bundle, and this is automatically finite. And why is it finite? If you look at a fiber, that's just corresponds to the ideal where you take some subspace of I sub D of codimension 1, right? A point in PS is defined by all but one of the linear forms. The linear forms are just sections in I sub D, so I'm taking a codimension 1 subset and looking where it vanishes here. Of course, if I sub D has codimension R plus 1, then any codimension 1 subset of I sub D generates an ideal of codimension, the Krull codimension, R at most, so it's a finite set of points. So that's one way of seeing that any such morphism is finite. And so I'm in the setup where I can do this. And this theorem in that case says that this epsilon sub t, I guess epsilon plus 1 actually, is exactly the maximum regularity of the fibers of that morphism of projective space. So that's the common context. So corollary really is a special case. We would like to know something about epsilon. Well, epsilon plus 1 is good, so let's subtract the 1 from the other side. Epsilon is equal to the maximum of the regularity of the fibers of the morphism PR to PS by the series I sub D plus 1. It's interesting to even look at a more special case, if you can imagine a more special case, and look at the case where R is 1. So why is that a nice thing? It's because we understand so well the ideals, the points, if you like, or the finite subsets of the projective line. They're just polynomials. So still a finer corollary. If I in k of x0, x1, again corresponds to a finite morphism of P1 to PS. Let's say I has S plus 1 generators of degree exactly D. So choose your favorite s+1 forms of degree d, maybe monomials. And of course, in order for this to be a well-defined morphism, I has to be primary to the maximal ideal. So the GCD of I, in that case, you could say is equal to 1. That's what that means there. And you look at the regularity of I to the t. So I to the t contains x0, x1 to the td plus epsilon. And what is epsilon in that case? Epsilon is the degree of the greatest common divisor of subsets of S elements out of I sub d. So look at all S-dimensional subspaces of I sub d. Look at their greatest common divisors. That's the degree of those common divisors is the number of points in the fiber, which is the regularity of the fiber in that case. And so that's the number epsilon. Best epsilon is for large t. The best epsilon is the maximum of the GCD, of the degree of the GCD of, let's say, W in I sub d, codimension 1, plus 1. This is the regularity of the fiber, and so I have to add or subtract 1. Let's see, I think I added what I should have subtracted here, minus 1. Right? So it's a very primitive formula in that case, and surprisingly I don't know a direct proof, even in this very simple setting where it says something about the greatest common divisors of sets of polynomials. For monomial ideals, you can see very clearly the picture, and I think I won't do that. Let's see, I started at 40, didn't I? So I have another bit of time. All right, so it seems worthwhile, you know, I claimed that the motivation for looking at this whole picture was to prove something about regularity of varieties, and I had a conjecture about the regularity of the general fiber of a projection. So we should at least translate that conjecture, and let me tell you what it says in this new language, this algebraic language. So the situation of that conjecture was that I had this subvariety, an n-dimensional, now I do have an n subvariety in PR, and I wanted to project it, let's say, to a hypersurface. We could project to other dimensional spaces as well, and the same kind of machinery will say something, but it's confusing enough to stick with one number. So let's project, it's only a rational map here, to P n plus 1. So here's the map phi. And if I project from a general center, phi is projection from lambda, let's say, lambda general of whatever the correct dimension is. Then this will be a well-defined morphism. It will be finite, and I'm interested, very interested, in fact, in the regularities of the fibers of that morphism. So how do we express this algebraically? Using this machinery here, we can say it in the following way. Such a morphism really, well, first of all, x corresponds to a homogeneous coordinate ring. So x corresponds to Sx, let's call it. That's S, the polynomial ring, modulo the ideal at X. The projection corresponds to a choice of n plus 2 linear forms in Sx. That's really what it is. X is dimension n, Sx is dimension n plus 1. So it's rather natural to take n plus 1 linear forms. That's a system of parameters. I want to take n plus 2 linear forms. So let's take L1 up to L, or L0 up to Ln plus 1. But remember, this is one more than the dimension of Sx, n plus 2 linear forms, general ones. They generate some ideal I. We can think of it inside Sx instead of inside the polynomial ring. It doesn't really matter here. And thinking of it inside Sx, I want to take its powers and compare those powers to powers of the irrelevant ideal generated by the x naught up to x r. So I to the t, once again. Now in this case I is generating degree 1, so the expression simplifies, and what I expect to see is that I to the t has regularity t plus epsilon sub t, where the epsilon sub t are decreasing. I to the t, regularity of I to the t equals t plus epsilon sub t. And now regularity as a what? Well, regularity as an S module, of course, but it doesn't really matter. There's the theory, one of the good things about regularity is that it's very robust, sort of invariant. It doesn't much matter where you compute it or with respect to what ring. And so, in fact, you can check that for large T, this is equal to the smallest number. So that I to the t contains, again, the maximal ideal, the irrelevant ideal in Sx to the t plus epsilon. You have to get sufficiently high in t to make this true. So this equality is already for t large, smallest, such that this is true. So we compare powers of I with powers of the irrelevant ideal, and now the assertion we want, the conjecture that I made before, which would lead to an improvement in our knowledge of regularity of projective varieties, would say that I to the t actually contains m to the t plus, I believe it's n, I'm a little off between n and n plus 1. Let me think about this for a moment. If I yes, that's right, m to the t plus 1. So for instance, if I have a curve, if x is a curve, Sx is two-dimensional, I'm taking 3 linear forms, and the true assertion in this case is that a sufficiently high power of the ideal generated by those linear forms will contain the one higher power of the irrelevant ideal. That's the statement that the image of the curve has only nodes as singularities under a general projection. So this is true at least when x is isolated, well, when x is smooth, over the complex numbers for n less than or equal to 14, which, as I say, you might think is pretty strong evidence for a thing like that, but we don't really know in this case. So I know no algebraic proof of this. This n less than or equal to 14 stuff goes through Mather's transversality theory for jet bundles, multi-jet transversality. Very strong and very different looking theory than this one. So this is Mather. I don't want to claim any credit for this. I find this result very attractive. It looks like the kind of thing that commutative algebraists prove, and I'm hoping that one of them will prove it. But so far...
What is the fiber?
So the fiber regularity would be n plus 1. Yeah. The fiber would be bounded by n plus 1. I'm not saying that this is sharp. I'm just saying that this gives me an upper bound on the regularity of I to the t. And this corresponds to the upper bound on fiber regularity at n plus 1. So if this is true in either its geometric form or this algebraic form, then the kind of thing that one would prove using the methods of Castelnuovo and that Professor Kwok has developed would be something like this. If true, then the regularity of x in PR smooth then if you have x in PR smooth, then the regularity of x would be bounded by the degree of x plus a constant that depends at least only on the dimension of x and on R. And the constant is not so bad. It's a nice computable number. I won't write down the formula. But you can find it in my paper with Roya, if you like. So, yeah, well, mostly conjectures, but there you are. This reminds me a lot of the Briançon-Skoda kind of theory that has been developed in commutative algebra, and its connections with vanishing theorems is very strong, so it smells like the right kind of thing that one might be able to prove. Well, I left open the question of epsilon. How big do you have to take t to make any of these things true? And of course, if you are interested in examples, you might want to compute epsilon, and you can't compute epsilon unless you know how big t has to be. So that's a kind of burning question for me. So you might say, you know, are we at infinity yet? That's the kind of question my children ask me when we're driving somewhere. All right, so how can we do that? Unfortunately, the answer is nobody knows, except in this very special case, not with the m equals s, but I'm going to assume m equals s just for simplicity. So the only time that we know a bound, any bound, I think, explicitly on the t that you need to take is in this case when I is generated by forms of a single degree and contains some power of the irrelevant ideal. And you can take a module if you want, but I'll do it without the module, just to simplify the notation. So in that case, the situation is this, and it's an interesting algebraic situation, I think. So inside S, again, I'll say one more time, then I'll stop saying it over and over again. You could do everything I'm about to do with an auxiliary module, but it would just make the notation more complicated. So inside S, you have I sub d, I generated by I sub d, let's say. M primary, so it contains a power of m. And then there are several rings which appear naturally. For example, you might look at the ring which corresponds to the image. This is the case where x is equal to PR. And you might look at the ring which corresponds to the image of x in general or to the image of PR in this special case that I'm taking. And that's called the fiber ring, x k of ID. So ID is the subspace of a ring, so you can square it, and cube it, and you get a graded ring by taking powers of ID. I sub d means the degree d part of I. So that's the actually the ring of the image of this map, phi of PR in our case. But you can also look at some submodules of S. For example, you could take the degree E forms in S and look at the module they generate over this subring. So you can look at, let's call it M sub E is equal to K of ID times S sub E. I've seen this ring a lot in my time in commutative algebra. I haven't seen this module very often. There's a sequence of modules there, one for each E, sitting inside SE. They overlap quite a lot. Each one is a summand of S as a K of ID module, but they're not mutually compatible with each other. However, the direct sum of them is isomorphic to the Rees algebra of I. So you can take the Rees algebra of I, that's by definition S of, let's say, I times T inside inside a polynomial ring in one more variable. I shouldn't use T, let's say Z, S of Z. And you can compare these with that. This is actually the V. In this situation, this is also a module over K of ID, which is a sub-algebra of it. And this is actually the direct sum of the M sub E's as K of ID modules. So that's a sort of fine structure of the Rees algebra, which holds just in this case when I is generated by forms of a single degree. Now, in general, you can write the Rees algebra as, well, the polynomial ring S, and then some new variables corresponding to the generators of I, y1 up to y, whatever it was, S plus 1, I guess, y0 up to y little s. In my notation, these correspond to generators of I. Excuse me. And this is, of course, an algebra over the polynomial ring in the new variables, k of y0 up to ys. All right, so this is a long introduction to the following rather small theorem, which I proved with Bernd Ulrich, which says that if you measure the regularity, the Castelnuovo-Mumford regularity of this algebra as a module over this subring, so take a bigraded free resolution of this and forget the gradings by the x's and just count degrees in y's. That's one way to measure the regularity, the y regularity. Then that's a bound for how high you have to go in t before you get stabilization. So if t is at least as large as the y regularity of r of I, then I to the, well, yeah, it's exactly true as I'm saying it. I to the t contains m to the dt plus epsilon, where epsilon is the stable value. The asymptotic regularity. Now, this is a very computable thing. If you have a copy of Macaulay on your laptop, then you whip it out and you type Rees algebra, and then you say Rees algebra, or you just say regularity with respect to the grading, where the y's have degree 1, the x's have degree 0 of this algebra, and you get a number, which is this number. So this is quite a computable and reasonable thing to look at. On the other hand, it's not nearly as simple as some, because you have to look at the whole Rees algebra, as something like k of id. And we've done quite a few computations which show that a much simpler statement might be true. So, the last conjecture, which ties all these n sub e's together, the regularity of n sub e is a decreasing function of e, so is bigger than or equal to the regularity of n sub e plus 1, and in particular, the y regularity of the Rees algebra, the number that appears over there, is equal to the, if you like, ordinary regularity of this ring of the image, k of id. So I can't prove that, but it's true a lot of the time. There must be, if it isn't true in general, then there's some nice hypothesis which makes it true. Again, I'm only talking about the case where I is generated in a single degree and contains a power of the maximum ideal. But we could put in a module everywhere, or a homogeneous coordinate ring everywhere to do this with as well. Well, as you see, there are more questions than answers in this subject, but that makes it fun to think about. Thanks for your patience.